so this is going to be a short video over the different types of collisions that we can have. And this is specifically in a momentum kind of sense. So we know things hit each other, but there's a lot of different ways that they can hit each other, and the outcomes that come after the actual collision can be different depending on what kind of collision it is. So we basically have two different types of major collisions, and that is elastic, and then we have something called inelastic. Alright, so we have elastic and inelastic. Okay, now this is basically how you can differentiate the two of them from each other. Inelastic means they are going to stick together. Okay, so this is like the two cars having the Velcro sides facing each other, and so they hit each other, and the Velcros stick, and so you end up with one object moving after the collision. Elastic is kind of like, if you think about an elastic waistband or something else that has elastic on it, it's going to bounce, it's going to stretch, it's going to bounce, and so that's basically what happens. Now, there's a little bit more to the elastic than just bouncing, as we'll get to here in just a second. So what is that? Elastic. In order to be considered an elastic collision, you have to have two things. Momentum has to be conserved, so momentum is conserved, and that is true for everything. Everything has to have momentum conserved, and of course we talked about in class how you can have an outside impulse, and so technically momentum might not be conserved within the system, but as long as you're taking into account everything in the system, then momentum should always be conserved. The other factor that goes into an elastic collision is the fact that kinetic energy, specifically, kinetic energy has to be conserved. Alright, and I know what you're kind of thinking. Well, energy is always conserved. Yeah, that's true. Energy is always conserved, but that doesn't mean that kinetic energy is always conserved. You don't always have to have the same amount of kinetic energy before and after something happens. The ball rolls up a hill, for example. Kinetic energy is not conserved because it gets turned into potential energy. But in this case, we have to have a bounce, and it has to be in such a way that we have kinetic energy conserved. And so this is going to be like the two magnets on the cars facing each other. And so when you have that collision, there's nothing there that's going to catch on each other. There's no actual hitting, no energy loss due to sound, nothing like that. So this is going to be an elastic collision. So the basic one that we saw in class was that if you have one car coming in with a velocity and another car sitting here with no velocity, collision happens, then the first car is going to have no velocity, and then the second car is going to go off with that same velocity over here, assuming that they're equal. So whatever that other velocity happens to be. So it's like the momentum completely transferred from one object to the other. Okay. So does it always have to be like that? No. So let's take a look at a situation where the masses are different. So we have 4 kilograms here, and it is moving at 3 meters per second. Let's say it's just one of those cars. Okay, I know 4 kilograms is a lot, but we're just going to work in round numbers here. We have another car here that's 2 kilograms, and it is currently not moving. Now, you are not going to be responsible for having to solve a system of equations to try to figure out what these velocities are going to be. I'm going to go ahead and give you one of them. So, collision happens, and our 4 kilogram object, because it is more massive, after the collision is going to continue to run forward. It has a little bit more inertia, so it has 1 meter per second of a velocity after the collision. So the question is, what does the 2 kilogram object have in terms of its velocity? Well, remember that we can use that collision as our equal sign, so we have the same momentum before as what we do on the after, because momentum is conserved. So over here, momentum is mass times velocity, so 4 kilograms multiplied by 3 meters per second. And that's the only thing, because he doesn't have any momentum. The second car doesn't have any momentum. He's staying still. Over here, we have the 4 kilogram car moving at 1 meter per second, plus the 2 kilogram car moving at some velocity that we don't know. So, for going some units here, we have 12 is equal to 4 plus 2 times v. You can do some algebra, or you can just try to figure it out on yourself or on your own. If you subtract the 4 on this side, 12 minus 4 is 8, and you divide it by 2, so you end up with 4 meters per second. Now, is this truly an elastic collision? Because we have two different things that have to be in an elastic collision. It has to conserve momentum, which we just used conservation of momentum to find this 4 meters per second. So obviously momentum has to be conserved. Okay, we have 12 over here. We're going to have 12 over here, 4 plus 8. So is kinetic energy conserved? So let's figure that out. Kinetic energy on the before side, we only have the 4 kilogram mass moving. So that's 1/2 times 4 kilograms times the 3 meters per second squared. And on the after side, both cars were moving, so we have to look at the kinetic energy for both of them. 1/2 times 4 kilograms times 1 meter per second squared. 1 meter per second squared. Plus 1/2 times the 2 kilogram object moving at 4 meters per second squared. More 4 meters per second squared. So let's see, 3 squared is 9. 9 times 4 is 36 divided by 2 gives you 18, so that'd be 18 joules. Do the same thing over here. 1 squared is 1, so this would end up being 2 joules here. And then over here, 4 squared is 16. And then the 2's kind of cancel out with the fractions, so you have 16. So in fact, you do have 18 equals 18, and so kinetic energy is conserved. And since kinetic energy is conserved, we can classify this as being elastic. All right. The next one is an inelastic, and they're actually much easier. Inelastic. There we go. They are much easier because the objects stick together. So if we have a mass of m, because not always are we going to be given numbers, sometimes we work in variables, and that has a velocity of, let's say, 4 meters per second, and it collides with an m that is not moving. Okay, there's the collision. Then on this side, we just have one object that has twice the mass. Okay, in this case, because both these objects were equal. So we know that if we multiply the mass by 2, so if mass is multiplied by 2, then our velocity is going to half. We saw that in class today. So what will the velocity be? Well, it'll just be 2 meters per second. Multiply the mass by 2, so the velocity's got to go down. That's because momentum has to be equal, right? Mass times velocity on one side has to be equal to mass times velocity on the other side. Velocity, there we go. So if we double the mass, we have to halve the velocity in order for that to still equal the mass times velocity on the other side. Now let's take a look at the kinetic energies. The kinetic energy on the first side was just 1/2 times the mass that was moving times 4 squared. On the other side, they were stuck together, so it's going to be 1/2 times 2m times the velocity there over there, and that's 2, so 2 squared. Again, on the left-hand side, 4 squared is 16 divided by 2, so that gives you 8 times m. We're going some units here. It would be in joules. Over here, we have 2 squared is 4, and then the other 2's kind of cancel out, so we end up with 4m. So that's not equal. So kinetic energy is not conserved. So again, we're talking about how total energy always has to be conserved. It's one of the hallmarks of physics, right? All energy has to be conserved. Well, so where does the energy go? Well, the Velcro has a lot of friction, the sound of the two cars hitting. There's something that we call mass deformation whenever you have a mass that's changing its size. And there's energy involved with doing that. There's work involved with doing that. So you throw the kinetic energy into other forms, like thermal energy, like sound energy, vibrations through the cars, that kind of thing. So kinetic energy is not conserved, but that doesn't mean that total energy is not conserved. So that's an that's an inelastic. Now you can have variations of these two. Actually, really, the elastic collision is the only one that has kinetic energy conserved. But you can have things that are not completely inelastic, which means they don't necessarily stick together, but they don't conserve kinetic energy either. And so that would not just be, that would be kind of a partially inelastic collision. But even in those cases, momentum has to be conserved. We always have to have momentum conserved. That's a thing about this unit. If momentum is not conserved, then you know that there's an impulse somewhere that's coming from the outside. Now, technically, there's one last collision, and it's not really a collision at all. It's called an explosion. Okay, this would be like putting those two cars next to each other with that little bar in the middle, and you push the button and they spring outward, and so they go out like this. But if they were not moving to begin with, then that means their total initial momentum has to be equal to 0 kilogram meters per second. which means the final momentum has to be equal to 0 kilogram meters per second. What does that mean? Well, that just means that, hey, we got some negative momentum from this guy, we got some positive momentum from this guy, and we know that the momentum over here has to equal the momentum over there in magnitude. They have to equal each other. If they don't equal each other, then you are doing something wrong. There's no conservation of momentum. So whatever the masses are, whatever the velocities are, you could have one that is 4 times the mass of the other guy. That just means that he has to have 4 times the velocity of this guy. So momentum is still going to be conserved. And that's an explosion. So it's not anything too great in terms of conceptual difficulty there. It's just a third type that sometimes gets thrown in there. But the hallmark of an explosion is that your momentum is always equal to 0 total momentum. All right. So we'll have some questions for you to be able to practice on this, and don't forget your lab that you're figuring out how to do.